Today I would like to talk about some specific aspects of absorbed dose delivery and boron quantification in neutron capture therapy. First of all, I would like to say a few words about binary radiotherapy at all, and why do we need these new methods of cancer treatment. From the medical point of view, from the point of view of oncologists, ideal depth dose distribution is can be seen on the left picture. It's a rectangular shape, and all the prescribed dose is set within the tumor volume, and out of the tumor in the normal tissues, the absorbed dose is 0. However, if we take a look at depth dose distribution of photon radiation, which is mostly used for radiotherapy, then you can see that its shape far away from the ideal one, and you can see that it has a maximum near the surface and shallow decrease to the depth. If you take a look at proton therapy or carbon ion therapy, you can see that a single particle dose profile can be compared to the ideal one. But if we have to deal with extended tumor with some length, with some volume, and we have to overlap separate profiles of the particles, then we inevitably lose this beautiful shape. And though on the right to the deep we have a very steep decrease in dose, to the left to the surface we still have a significant irradiation of normal tissues. To overcome this obstacle in conventional distant radiotherapy, several irradiation fields, multi-field irradiation is used. And this approach was pushed to the limits in stereotactic radiotherapy, where a huge amount of directions are used to deliver prescribed dose to the tumor. However, this approach is limited to the tumor size. If the tumor size is small, about 1 centimeter, then this approach is acceptable. However, if we have a tumor which is much larger, then we just have no enough directions to do proper irradiation. However, apart from multi-field irradiation, there can be another approach to deliver prescribed dose to the tumor. And this approach is binary radiotherapy. The basis of this method is to change absorbing capability of the tumor tissues, increase its stopping power, and thus absorb more radiation in tumor than in the surrounding normal tissues. This enhancement can be achieved by injection, by administration, specific pharmaceuticals, which contain some agents capable absorbing external radiation. And for binary radiotherapy, the strategy of its application for curing cancer can be expressed in this way. If we have a tumor, a patient with tumor, we can administer specific pharmaceutical. It's specifically accumulated within the tumor volume. Then this area is irradiated with a single fraction from 1 or 2 directions with external radiation, and local absorbed dose is delivered within the tumor, and we have a tumor regression. How this technically can be achieved? One of the methods of binary radiotherapy is neutron capture therapy. It's, I would say, the most known, and it was the first method of binary radiotherapy. And as you can see from its name, it's based on application of neutron radiation. And when we're talking about neutron radiation, we should clearly distinguish two types of neutron radiation, fast neutrons and thermal neutrons. Though by its nature they are both neutrons, but they have different energy, and the way they interact with matter, with medium, is completely different. Fast neutrons interact in elastic scattering, in striking light nuclei, mostly hydrogen, and thermal neutrons, they interact with matter by means of nuclear reaction. And this is called neutron capture reaction. The number of that reaction is proportional to the number of thermal neutrons delivered to the target, and to the value is called cross-section of the reaction. This value determines the number of nuclear reactions that the neutrons can cause. And if we take a look at the table of some elements which comprise biological soft tissue, then you can see that such elements like such isotopes like 10 boron and gadolinium-157 have extremely large value of cross-section. It's several orders larger than for hydrogen, for carbon, for nitrogen, and thus placing these elements to the subject, to the tumor, we can selectively make external radiation, make neutrons absorbed, particular at that place. Today we'll talk on mostly on boron. You can see neutron capture reaction of 10 boron, and it has some favorable features. As a result of this reaction, charged particles are emitted, alpha particle and lithium-7 particle. These are short-range particles, and all the energy is absorbed within the tumor cells, within about 10 micrometers. And that makes neutron capture therapy extremely selective method of killing tumor cells. And if we place 10 boron nuclei only in tumor cells and irradiate all these cells with thermal neutrons, then only cancer cells will be killed and the therapeutic effect achieved. If we take a look at the absorbed dose components in neutron capture therapy, we can see several components. These are components, these are fast neutron absorbed dose, which is created by fast neutrons, which inevitably present in a thermal or epithermal neutron beam. Nitrogen dose, which is created by nuclear reaction of on nitrogen, and as a result of this reaction, proton is emitted and also cause absorbed dose within the irradiated object, and dose from photon radiation, mostly from neutron capture reaction on hydrogen. But also some photons are coming within the beam of thermal neutrons. And of course, it's a dose from the reaction on boron-10. If you take a look at different components calculated by Finnish researchers, you can see that the largest components are photon and boron. And boron component depends on boron concentration. This picture presents boron dose for 15 ppm, 15 micrograms per gram of tissue. And this value is, I would say, crucial because for this concentration of boron, boron dose is equal to the rest of the components. And starting from that particular value, boron dose comprise 50% of the total dose. And on increasing that dose, we can reach up to 90% of the dose within the tumor created by the boron. That is why it's so important for boron neutron capture therapy to evaluate boron content in tumor and normal tissues. And again, let's compare depth dose profile. On the right, you can see data by Finnish researchers, but for much larger concentration of boron, that is 50 ppm. That is quite usual concentration for brain tumors, for example. Calculated with the assumption that the tumor to normal ratio is 3. That is, the concentration in tumor is 3 times larger than in surrounding normal tissues. And you can see that this depth dose distribution is approaching to the ideal one. And if we start increasing the concentration of boron within the tumor and increasing the concentration within the tumor and decreasing in surrounding normal tissue, we will achieve almost ideal distribution. I would say a few words about methods which are used for boron quantification. For BNZT, it's necessary to detect boron in concentrations higher than 1 ppm. The method should be applied for biological samples. And the method should be quite fast, about 10-15 minutes, because the evaluation of boron concentration should be made in the process of the therapy. And on that concentration, physicists and medical staff should make the decision on the time of radiation and on the necessity of the BNZT procedure at all. Boron has no chemical methods for its information, so only its physical properties are used to detect and quantify boron. And methods which are used in current and past clinical trials are based on atomic properties of the boron atoms, mostly its mass and electron shell structure. These are mass spectrometry and optical spectrometry, and on nuclear methods based on nuclear reactions which occur with boron nuclei. That is from gamma neutron activation analysis and neutron activation autoradiography. I would say briefly about these two methods to make sense of the complications and possibilities for boron quantification. First, I would like to say on nuclear methods. They were historically the first one applied for boron quantification in BNZT, and it's quite understandable because first researchers dealing with boron quantification and BNZT, they have neutron beam as a compulsory component of BNZT, and it was easier for them to perform analysis with nuclear methods with neutron activation application. Neutron capture reaction 10 boron is accompanied by emission of gamma quant with the energy 478 keV, and as I've already said, charged heavy particles. Gamma quants is used for detection and boron quantification in prompt gamma neutron activation analysis. These quants are detected by detectors. We've got energy spectrum of radiation, and by corresponding boron peak by its height and its area, we can calculate actual concentration of boron within the measured samples. Another approach is autoradiography, which is based on detection of charged particles, and for that polymeric plates are used When charged particles are entered the volume of that plate, they create chemical damages, and these damages can be revealed with etching, forming visible in microscope or optical microscope tracks. The number of tracks is proportional to boron quantification. The advantages of autoradiography method is quite sufficient detection limit. It's quite sensitive, so it matches the requirements of BNZT, and it's of very low cost because it has no any consumables. It doesn't require any expensive equipment. Polymer detectors, track detectors, they are very cheap, and etching components is usually potassium OH. So it's a method of choice for students. However, these methods can be applied only for samples. It cannot be applied for living organism, and it's quite it requires some time because etching is time-demanding process. From 2 to 3 hours, and it cannot be used as a fast method for quick boron assessment. Boron gamma neutron activation analysis has a similar detection limit. Its advantage that it's non-destructive. Sample doesn't need to be pre-processed, so it can be measured as it is. It has comparatively low cost of analysis because it has it doesn't require any consumables. It's comparably fast. It depends on the boron content. If we have quite significant compounds, let's say 50 ppm or even 100 ppm, then the whole analysis will be around 10 minutes. However, if we have to measure lower concentrations, about several ppm, then it may require several hours for data acquisition. And another advantage of this method is possible application for in vivo measurement. The only disadvantage which I can see is that it requires a custom design facility for every particular neutron source, for every particular BNZT center. So it's hardly to be standardized to make it as a commercial product. Another methods, these are atomic methods of boron quantifications. They are well known and they are used in a variety of scientific fields. These are mass spectrometry and optical spectrometry with inductively coupled plasma. This method is based on detecting some properties from ionized atoms or the sample. The sample, which contain boron and other elements, is injected into plasma talk. And then there are two opportunities. These ionized atoms are delivered to mass spectrometer, and we've got a spectrum by mass to charge ratio. Or these ionized atoms emit on the excitation of the electron shell's specific light of specific length, and this in turn can be detected and corresponding spectrum can be obtained, thus quantifying the elements in the sample. This method has, both these methods have extremely high sensitivity. They can detect boron in a ppb that is 3 orders smaller than necessary for BNZT, and comparatively they can perform it quite quickly. And the limiting stage of this method is sample preparation. They definitely require sample preparation. If we deal with blood plasma, as it's usually done in BNZT, then it requires almost no sample preparation. But if we have to digest soft tissue samples, then it can require time. Again, these methods can be used only for samples for ex vivo analysis, and they require a lot of argon to form plasma talk, and that's make it comparatively expensive method. But that is the method which is used in all modern clinical trials in BNZT. During practical implementation of BNZT, when treating patients, the procedure of boron quantification currently is the following. Every patient on administration of boron drug, no matter which one, are sampled with the blood every 10-20 minutes, and they are immediately analyzed for boron quantification to create a time-dependent curve on boron concentration. The goal of this procedure is to evaluate average boron content in blood during the radiation. And it can be quite specific for every particular patient. So individual profile of boron concentration in blood is usually created. But then the calculation of boron content in tumor and surrounding normal tissue is quite simple. For decades, the only approach was to multiply boron content in blood on a specific fixed value, which is tumor to blood or normal to blood ratio. And that value were obtained in some clinical trials with sampling of normal tissues and tumor tissues on preliminary surgical removal. Of course, this is a very rough method, and the scientists were not satisfied with it. However, up to the beginning of 20th century, that was the standard approach for boron quantification in tumor and normal tissue. But later, Japanese scientists developed additional pharmacokinetic model to calculate boron content in tumor and tumor tissues and normal tissues based on the boron concentration in blood. And you can see the example of this pharmacokinetic model application by Finnish scientists. Dots are measured values of boron concentration in blood, and these curves are corresponding to normal to concentration of boron in normal tissue and in tumor tissues. For evaluation, used quite simple pharmacokinetic models to simulate, to feed experimental data of boron content in blood to compartment, open compartment models are used. So they are quite simple and well known. To calculate boron content in tumor based on the plasma content, blood plasma content of boron, a closed three-compartment model was developed by Japanese scientists, and they used quantification of boron using PET with labeled boron compound, and I will talk a bit about this later on. What is the disadvantage of this approach? Every pharmacokinetic model which is developed is valid only for particular type of cancer. And that model that were used and which I described on the previous slide were developed for brain tumors. If you apply BNZT for some other type of tumors, then you have to develop, you have to gather some experimental data on distribution of boron distribution, and you have to develop new pharmacokinetic model. Boron quantification with this pharmacokinetical approach is semi-personal, let's call it this way. because though data on blood content are quite personal, measured for an individual patient, the ratio which defines the boron content in the tumor is based on average data. And of course, these can lead to errors and overestimation or underestimation of boron content for every particular patient. And additionally, current pharmacokinetic models provide only uniform boron distribution. And that is, in fact, not true, because boron distribution, the distribution of boron pharmaceutical can be heterogeneous. And thus we're not evaluating possible hot and cold spots in tumor tissues and normal tissues. Thus, we can cause damage of normal tissues, or vice versa, we can unirradiate necessary areas of tumor and cause recurrence by that. So direct instruments of boron content assessments are extremely necessary for the development of BNZT and improving its therapeutic efficacy. There are two approaches. These are direct boron detection and direct boron imaging, and indirect boron detection when we are detecting not boron atoms or nuclei, but we detect the whole compound which contain boron. First, I would like to say about magnetic resonance imaging. It's a well-known medical modality, diagnostic modality. Usually it's used to image protons, hydrogen, but it can be applied for boron imaging as well. Boron consists of, boron has two stable isotopes, that is boron-10 and boron-11, and they both have magnetic moments, and in theory can be used for MRI. You can see in the table their spin value and magnetic Guericke ratio, and you can see that's comparing to hydrogen, they are, let's say, worse. Especially their magnetic Guericke ratio is very low. Their excitation signal decays extremely fast, and standard equipment for MRI for hydrogen imaging cannot be used for boron imaging. So special protocols, special radiofrequency coils are necessary to perform boron imaging. Boron-11 was imaged first, and you can see the example of its imaging. A patient with resected brain tumor was administered with BSH boron-containing drug, and you can clearly see that is a proton image, and that is a corresponding boron image. And you can see that by the borders of resected tumor, you can see accumulation of boron pharmaceutical. And here you can see a reference tube with boric acids to show somehow to evaluate the intensity of the signal. This imaging was performed for quite low space resolution, about 7.5 millimeters. It's very large voxels comparing to hydrogen images. But the data, the acquisition data was performed for 9 minutes. That is quite a reasonable time on a 1.5 Tesla scan. The authors decided that the boron-11 can be imaged with this equipment starting from 25 ppm. That is not an ideal value for BNZT. However, it can definitely reveal the therapeutically significant amounts of boron in normal and tumor tissues. The attempts of exactly 10 boron imaging with MRI was also performed almost 10 years later. It was made on a much more powerful scanner with a magnetic field of 4.7 Tesla. The spatial resolution and acquisition time was somehow comparable to the previous research. And you can see that on the left there is a proton MRI image, and on the right corresponding map of boron content. You cannot visualize with boron any anatomical structures, but for the purpose of absorbed dose evaluation, that is quite enough. This particular study reveals no significant accumulation in tumor, but you can see quite beautiful signal from the bladder. What is the advantage of MRI application for boron quantification? First of all, there's no ionizing radiation. You can ask, why should we think of using or not using ionizing radiation in case of BNCT, which is no doubt the modality, the methods which uses ionizing radiation to treat patients. However, we should think not only about the patient, but about the medical and technical staff. And they are also exposed to ionizing radiation. So if we can exclude some stages of BNCT procedure from ionizing radiation, that would be great. So the absence of ionizing radiation in MRI imaging is an advantage of this method. And another method that it's direct boron determination, direct boron imaging. It doesn't depend on a particular pharmaceutical. It's work and can quantify boron in any case. The disadvantage of MRI application for BNCT for boron quantification is that MRI is mostly qualitative method. Every time we place an object into the scanner, it's normalized signal, it recalibrates itself, and we can compare intensity signal only from the single set of scans. If you put the same object slightly different way, then the signal will be different. And that's make quantification of boron with MRI is quite a tricky task. And it's require additional development of a special equipment, expensive equipment, which is not good for BNCT for medical application. Particular disadvantage of boron-11 MRI image is that boron-11 is not a therapeutic agent for BNCT. And chemists all around the world are fighting to deliver as much boron-10 as possible. And pharmaceuticals, boron-containing pharmaceuticals for BNCT are enriched with boron-10 isotope up to 95, 98%. And it's not good to left some atoms in a pharmaceutical not enriched with 10 boron isotope, but left with boron-11. Another approach is indirect approach, but it also but it's also used, but also MRI is used for this method, is labeling of boron compounds with some marker. And here I would like to present the results of Italian researchers. They labeled known boron-containing pharmaceutical boron phenyl alanine with fluorine-19, and this isotope can be considered exogenous because it can be found only in teeth and bones, and in most soft tissues it cannot be found in a significant amount. So it can be used as a marker for BNCT. It has very similar magnetic properties to hydrogen. And this isotope can be imaged with the same equipment as hydrogen. And this image was obtained with a 7 Tesla MRI scanner. It's a scanner for animals. The only change is in changing protocol of data acquisition and tuning radio frequency coils for fluorine-19. Advantages and disadvantages of this particular approach, they are somehow similar to the direct boron detection with MRI, that is no ionizing radiation. Particular to this method, that is possibility to be implemented in a standard MRI equipment. So there is no need for hospitals to purchase and for manufacturers to develop a new equipment. The second, not the second, it's already the third method. It's radionuclide labeling. It's currently it's a method of choice for BNZT, and it's based on labeling boron pharmaceuticals, like here you can see the example, again, boron phenylalanine, labeled with also with fluorine, but with 18 isotope, which is a positron emitter. And thus we can use this for radiopharmaceuticals in a standard PET equipment and detect its normal and tumor tissues, and comparing to MRI, comparing to magnetic resonance imaging, PET is more quantitative method, and it's allow a quite good quantification of the isotope intensity. And even it was PET with fluorine-18 BPA, which was used as input data to create a proper pharmacokinetic model to determine boron content in tumor and normal brain by means of boron content in blood. For PET, we should, when labeling some boron compounds with radionuclides, we should keep in mind that it should have sufficient half-life value to be able visualized within the whole BNZT procedure, that is several hours. Radionuclide itself might not change boron drug pharmacokinetic because some radionuclides can be very heavy comparing to the boron compound molecules. It can be attached to the drug quite good and not cleaved within the organism. And the procedure of labeling should be quite simple, because in a hospital, medical staff and radiochemists cannot perform a complicated synthesis, so it should be quite simple. The advantage of this method that it can be implemented again in the standard radionuclide imaging facilities like PET and SPECT. It's a quite quantitative method, and it's have very high sensitivity. Disadvantage is the usage of ionizing radiation. To implement this method, additional pharmaceuticals must be developed with all the regulations matched and all the permissions achieved. And one additional disadvantage of this method, that not every boron compound can be labeled with a particular radionuclide. For example, BSH, which is the second popular boron-containing drug for BNZT, it's not easy to label with fluorine-18. And the final method I would like to talk about is, I would say, my favorite method. That is development and of prompt gamma neutron activation analysis. It was suggested in 2000 by Kobayashi, and it's uses the same gamma radiation from neutron capture action boron to detect its all around the object, similar to PET. and measuring projections of this radiation emitted from the irradiated object, we can restore the number of events, of neutron capture events on boron within the irradiated objects. Some calculations performed also by Japanese scientists show that for spatial resolution of 10 millimeters, boron can be detected starting from a concentration of 10 ppm. That is quite enough. And another advantage of this method that's measuring this method can measure not only gamma radiation from boron but also from hydrogen, and these two reactions can quantify dose, boron dose, and gamma and nitrogen dose, and that allows us direct absorbed dose measurement. And taking into account that these three components comprise about 97% of the total absorbed dose in BNZT, that is a unique opportunity for BNZT to measure absorbed dose within the patient directly and individually. So no phantom measurements, you can clearly detect what particular patients, what absorbed dose was delivered to these particular patients. However, unlikely that these methods will be used for BNZT planning, because it's required quite significant amount of boron to be administered within the patients, and it caused quite significant radiation load on the patient. So it's mostly the method to measure absorbed dose during the BNZT procedure. So to summarize all the things I said, I would like to say that the task for boron quantification should be divided into two different tasks: treatment planning and absorbed dose evaluation. And for treatment planning, some MRI or PET-SPECT methods are preferable. For those evaluation, PET-SPECT I think is the method of choice. Currently, PET is the most used method for BPA quantification. However, further drug development implementing maybe nano drugs, boron-containing nano drugs, can shift the interest toward single photon emission tomography as well, and maybe MRI. I think technical progress will definitely make huge progress in MRI imaging, and I think we will see new methods and new systems for 10 boron imaging with MRI, because it's very attractive method for boron quantification, especially for planning BNZT procedure. And all the researchers involved in drug development for BNZT should be focused not only on delivering maximum amount of boron to the tumor, but also keep in mind the way of its quantification, and maybe beforehand design the possible, develop the possibility of its labeling, maybe with radioactive marker or MRI marker. Thank you very much.